Hello students. Now today we are going to discuss about the design of sliding contact bearings, and in the last lecture we have started the design of hydrodynamic bearings. Now today we'll see the part 2 of the same. The learning outcomes of the today's lecture will be: students will able to understand the concept of friction circle. They will check the performance of hydrodynamic bearings using Raimondi and Boyd method, will determine the Sommerfeld number and its importance and role in the design of hydrodynamic bearings, to determine the heat generated in the bearings and the design procedure for the general bearings. If time permits, we will go for the one numerical. So we'll quickly recap what we have discussed in the last lecture. We have discussed, according to the Newton's law of viscosity, the shear stress at any point tau is given by mu A u upon h, where this mu is called as dynamic viscosity, A is the area, u is the velocity, and h is the distance. And we have seen the effect of temperature on the viscosity. As the temperature increases, viscosity decreases. The unit of absolute viscosity is centipoise. We have seen that when we are selecting this viscosity from the catalogs or the different tables or graphs available, in that graphs the value of viscosity is given in centipoise. So here you should have to remember the conversion of centipoise to the Newton seconds per mm square. So 1 centipoise is equal to 10 to the power minus 9 Newton seconds per mm square. The another important term, bearing pressure. The bearing pressure is given by bearing load to the projected area. W is nothing but the radial load acting on the bearing. A is the projected area given in Newton per mm square, where this projected area is given by L into D. We have also seen in the previous case the difference between the crushing stress and the bearing pressure. In case of bearing pressure, or bearing pressure is considered when there is a relative motion between the parts, and crushing stress is considered when the two parts are stationary. We have also discussed about the Patrov's equation, and Patrov's equation is used to determine the coefficient of friction of the lubricating fluids, and its relation is F is equal to, that is coefficient of friction, 2 pi square mu n upon P into R upon C. The variation of this coefficient of friction with operating values of bearing characteristics number. We have also discussed last time about the bearing characteristics number, that is mu n upon P, and that relation or the graph which is obtained by the experimental verification or experiments done by Mackey brothers, and that is known by the name Mackey's investigation. And the Mackey's has given the equation as the coefficient of friction F is equal to 2 pi square mu n upon P into R upon C plus alpha, where this alpha is called as leakage factor. The factor, that is bearing characteristics number mu n upon P, is help to predict the performance of the bearing. We have discussed in detail how this the graph that is obtained by Mackey's by the name Mackey's investigation help us or predict the performance of the bearing, and that we have seen with the help of bulk modulus K, where the bulk modulus is nothing but where the value of coefficient of friction is minimum. That point is called as bulk modulus. And we have also seen when your bearings should not be operate near the value of bulk modulus, and when we are designing the bearings are subjected to impact or fatigue loading, at that time the value of that bulk modulus should be 15 times than that of mu n upon P, 15 times bulk modulus. Okay, and this mu n upon P curve is important because it defines the stability of the hydrodynamic general bearings, and it helps to visualize the transition from boundary lubrication to fixed lubrication. So while studying this curve, which we have seen how the transition of this bearing is from stable to unstable or unstable to stable taking place, that also we have seen in the previous graph. So now to begin with, the first term, which is we called it as a friction circle in the journal bearings. So here, to understand this figure, this bigger diameter is nothing but the diameter of the bearing, and the smaller one is nothing but the diameter of the journal. This journal is subjected to radial load W. So here W is the radial load acting on the bearing, and when this bearing is at stationary condition, this shaft would be over here or journal would be over here. So it starts now rotating, and because of this rotation, there is a friction between the journal and the bearing is taking place. And here that is shown by the normal reaction. So this is the normal reaction taking place. Fr is the frictional force. So if you can see over here, here is the normal reaction Rn, this is the frictional force Fr, and these two I have drawn one resultant. So this is the R is nothing but the resultant force, and the distance of this resultant force from the center of the journal is denoted by x, and that x is called as radius of friction circle. So taking to this radius, if you draw a circle which will be smaller than this journal can be called as a friction circle. So to find out the relation or the function on which this radius of friction circle is depend, that now we will see. So here this is in the enlarged view I have shown. This is the W and this is the resultant R, and distance between that two is nothing but the X. Here this is the normal reaction drawn. This is the resultant force R, and this distance is X. Now this angle will consider as a theta. So the couple X, because of this force W with respect to this one point is given by W into X, where X is nothing but the friction circle radius. From this figure, we can write sin theta is equal to X upon Rn. This is Rn, but this theta is very small. Therefore, taking that theta sin theta is equal to theta. Again, as this theta is very small, and if you take the value of tan theta, then it again becomes very small. So in this case, it can be taken as tan theta. But we have seen while studying the friction, in the case of friction, the value of tan theta is generally taken as equal to the coefficient of friction. So here tan theta is equal to coefficient of friction. So F is the coefficient of friction. So we are taking this value. So we can write for this figure as tan theta is equal to X upon R. So this here it is the radius R is actually shown. So this is the tan theta is equal to X upon R, where R is the radius of the journal. So substituting in this case, what we can write, X is equal to tan theta into R. But tan theta is what? We have taken it as a F. So substituting this tan theta is equal to F, coefficient of friction. So we have got this X, the friction circle radius equal to F into R. So students, here you have to remember the very important term is that the friction circle radius is the function of coefficient of friction and radius of the journals. You feel absurd, or if you refer the question papers of competitive exams, GATE, IES and all, you may find that these type of questions on the friction circle radius are repeatedly asked. So here you should have to remember that the friction circle radius is function of coefficient of friction F and the radius of the journal. Now to move on, we'll see the Raimondi and Boyd method. So what is this method? This method is used to check the performance of bearings expressed in terms of dimensionless parameters. So Raimondi and Boyd has defined so many dimensionless parameters, and these dimensionless parameters are useful while designing the hydrodynamic bearings. and the values of these dimensionless parameters are available for full journal bearing with side flow in the table which is given over here. So here now we will refer in the latter case when we solve the numericals how to use this table, but just to understand this table, this is the dimensionless performance parameters for full journal bearing. This is particularly called full journal bearing, or we also call it as a 360 degree journal bearing. So here is L by D ratio is given, length of bearing to the diameter of the bearing is 1. This is the obligate eccentricity ratio. This is HO upon C. It is a one dimensionless parameter we have discussed. Sommerfeld number we are going to discuss now. Obligatory ratio, not obligatory ratio, but this is angle. Then R upon C into F QA upon RC NS into L, and what is all these terms now one by one we are going to discuss. So again the basic terms that we are going to use, we have discussed the things in the previous lecture. Again we will quickly review the terms. The small r is the radius of the shaft or the journal and its diameter is D. Capital R is the radius of the bearing and its diameter is capital D. Here you can see that term now. So L is the length of the journal or the bearing. C radial clearance R minus R. C1 is the diametric clearance, that is D minus D. E is the eccentricity between center of shaft and the bearing. Here in this figure you can see this is the O is the center of the bearing, O dash is the center of the journal, and this distance is eccentricity E. W is the radial load acting on the bearing. HO is the minimum film thickness of the fluid. Eccentricity ratio is given by E upon C, and C1 upon D is given by diameter clearance ratio. So again referring to this figure where this is the diameter of the journal, diameter of the bearing, and the radius of the bearing is nothing but capital R. Here this is the eccentricity distance between the centers of the bearing and the shaft, which is given by E. Then this is the radius of the journal, which is small r, and here this is the HO, and this line is called as line of action along which the action is taking place, and this is the radial load which is acting in the downward direction. So if we write for R is equal to summation of HO plus R plus E, which is written over here, and if we rearrange the terms, E is equal to R minus HO, but R minus R is nothing but the radial clearance. So substituting at radial clearance C minus HO. So eccentricity ratio is given by E upon C, where we know what is the value of E is C minus HO. So that is C minus HO divided by C. So 1 minus HO upon C. So this eccentricity ratio is given by 1 minus HO upon C, and where this HO upon C we called it as a minimum film thickness variable. So the table just now we have seen. So this is the table which we have seen where this term is HO upon C. So I have tried to highlight one by one the terms. So here that HO upon C is highlighted. So from the table we are able to find out the value of minimum film thickness variable. Here if you can see in the figure, this load W which is acting in the downward direction makes an angle with respect to line of action, and that is called as the phi, and the phi is called as attitude angle, or it is also called as angle of eccentricity. So what is the role of this angle? This angle locates the position of the film thickness with respect to direction of the load. Now the next and very important term in case of sliding contact bearing is Sommerfeld number. Students, you should have to understand the term Sommerfeld number. You should have to remember its equation, because in all the exams, competitive exams also, most of the questions on the sliding contact bearings are asked on the Sommerfeld number. So it is very important to understand the term Sommerfeld number. So what is this Sommerfeld? Sommerfeld was one of the scientists, and he has developed this equation making some modifications in the Patrov's equation. So from the Patrov's equation onwards, the Sommerfeld number has been developed, and it is a dimensionless parameter used extensively in the design of journal bearings. So it has very major role in the design of journal bearings. And why it is important in lubrication analysis? Because it contains all the variables normally specified by the designers. And this equation S is given by mu ns upon p into r upon c bracket square. Now try to understand the meaning of each and every term. Mu, it is the absolute viscosity of the lubricant in Newton seconds per millimeter square. Remember, it should be in Newton seconds per millimeter square. Ns is the journal speed in revolutions per seconds. P is the bearing pressure that is given by load upon area, W upon L into D. L and D are the length and diameter of the bearing. R is the journal radius and C is radial clearance. Remember, C is nothing but the radial clearance. And again, from the table, we are able to find out the value of S. Why this Sommerfeld number is important is just we try to understand the term. Here, this HO we know as this is a minimum film thickness, or it is also called as a minimum gap to be maintained to avoid the metal to metal contact. So why this why this HO we should have to maintain to avoid the metal to metal contact, that we try to understand, and this is the why this Sommerfeld number is important. It will refer this the initial position of the journal and the bearing where R is less than W. So the sound fluid is over here, and once this both are equal, so this comes to stationary position. So load is acting in the downward direction and the frictional force is acting. So once it is starts rotating, and when it is starts rotating and it is having some metal to metal contact between these two, so the normal reaction is acting in this direction. Here again R is equal to W and frictional force is also acting, and because of that there is a no minimum film thickness or no wedging action, and because of that there is a continuous metal to metal contact is taking place. And as the speed is go on increasing, there is a tremendous increase in the heat in the bearings, and as you know, as the temperature is increasing, after some time your bearing may get fail, and that is the reason why you should have to maintain some minimum gap here. Another terminology is Sommerfeld number is plotted. So HO upon C versus Sommerfeld number graph is plotted, and this graph is plotted for different values of L by D. Here if you can see is L by D, and this table is available for L by D is equal to infinity, 1, 1 by 2 and so on. So here if you can see L by D is infinity, L by D is 1 and L by D is equal to 1, and from this graph we are able to find out the feasible reason for the design, and your minimum load and maximum load should be within this range, and that gives you the idea for the selection of the bearings, Sommerfeld number also. Now the next and important terms are coefficient of friction variables, that is denoted by CFV, and here this is the term in the table is given by the term R upon C into F, which is called as coefficient of friction variable. So F is nothing but here coefficient of friction, R is we know radius of the journal, and C is the radial clearance. So we know the value of this coefficient of friction. From this equation we can calculate. So we'll calculate the frictional torque, that is nothing but the coefficient of friction load into the distance. So Newton per millimeter. So from that power we can calculate as a frictional power 2 pi nt, and here it is 2 pi ns. So 60 is not there. So 2 pi ns Tf frictional torque Newton millimeter per seconds. So substituting the value of this Tf, will get 2 pi ns into Fwr, that is in Newton millimeter. So we have converted into Newton meter, so multiplied it by 10 to the power minus 3. So this Newton mm becomes Newton meter, and this Newton meter is nothing but a joule, and when it is a joule, so joules per second is watts, and that's why I have written it as a or. So Newton meter per second is a Newton meter is a joule, and joule per second is a watts. So here 2 pi ns into Fwr, again this kilowatts is converted into kilowatts, so multiplied it by 10 to the power minus 6. Therefore kilowatt frictional power is given by 2 pi ns F W R into 10 to the power minus 6. So you should have to remember the equation for generation of frictional power. The next term is flow variable. So again, if you refer the table, here you will get the value of flow variable. So this flow variable is given by Q upon R into C into NS into L, where Q is called as flow of the lubricant and the unit is millimeter cube per seconds. R is the radius of the journal, C is the radial clearance, NS is the speed in RPS, and L is the length of the bearing. And where in the second equation we will get Qs upon Q, which is useful to find out the side leakage, where this Q represents the total flow of the lubricating oil and a part of which is circulated around the periphery of the journal, while the remaining oil flows out as the side leakage and given by Qs. So these are the different terms or the different dimensionless variables are defined by the Raimondi and Boyd method, and all these variables are listed in the graph for the full journal bearings. Now we'll see how this heat is generated in the journal bearings and how one can decrease or get dissipated or carried away the heat generated in the bearings. And you know, in the sliding contact bearings, because of the fluid friction, there is a friction taking place and the friction of the parts, the heat is generally generated. So if you try to understand this figure, where this is nothing but the journal diameter and this is nothing but the bearing diameter, this is the bearing, and between this journal and the bearing, this is the lubricating oil or the lubricating fluid. So the temperature of the lubricating fluid is given by T0. The temperature at the outer periphery of the bearing is given by Tb, and Ta is the atmospheric temperature. So whatsoever heat is generated over here is taken by the lubricating fluid. That lubricating fluid is transferring this heat to this bearing and it comes to the surface, and from the surface it is get dissipated to the atmosphere. So here it is shown as the heat dissipated. So here is the heat generation and here is the heat dissipation. So that total heat, now we'll assume that this total heat generated in the bearing is carried away by the total oil flow that is over here in the bearing. So these are the terms which we have just now defined, and from this equation where this Tb minus Ta, this temperature difference at the outer surface should be equal to the temperature difference at the inside the bearing, and from that we are able to find out the value of temperature at the outer surface. Then these are the notations. Hg we are using for the heat generation and Hd we are using for the heat dissipated. So how this heat is generated, that we have seen is because of the fluid friction or the friction between the two metals, and whatsoever is that friction is taking place, and because of that friction heat is generated. So what we can say, the heat generated due to friction is nothing but the power loss due to friction. And just now in this today's lecture only we have calculated the equation for the power loss, that is due to friction. So Kwf, that is equal to Hg. So 2 pi ns, coefficient of friction, radial load, radius of the journal into 10 to the power minus 6 is the heat generated. Now again in the previous method we have seen this is the coefficient of flow variable is given by the relation R upon C into F. So this equation will give you the value of coefficient of friction, that is CFP into C upon R. This side when it will go, it becomes C upon R. And we know W is equal to P into L into D. Bearing pressure is equal to W upon L into D. So here P into L into D, and D is nothing but the radius diameter of the journal or the bearing, can be written as 2R. So here it is PL2R. So we'll substitute the value of W in this equation, value of coefficient of friction in this equation, and this equation is get modified as this form. So Sg is equal to 4 pi ns into 10 to the power minus 6 into C P L R into CFE, substituting all these values. So this is the total heat generated in the bearing. So how this heat is get dissipated? This heat is get dissipated using this equation, HD is equal to HA delta T, where H is nothing but the heat dissipation coefficient, or we call it as a heat convective heat transfer coefficient, and the unit is watt per meter square degree Celsius. A is the surface area of the bearing, which is pi dl in meter square, and delta T is the temperature rise or temperature difference. So here, students, you just think of how you can increase the value of this HD. That you will understand by this. So what would happen if the heat dissipated from the bearing is greater than heat generated, means there is no problem of overheating. So no coolant is required. If both are same, then also there is no problem, so no coolant is required. And if the heat dissipated is less than heat generation, then what would happen? Continuously heat generation is taking place. Temperature of the lubricating will continuously increase, and it creates some problems to the bearing, and that time you require the coolant. So how you will increase this value of HD, that is heat dissipated? So if you look to this example, the equation, if the dissipated is HA del T, where H is nothing but the convective heat transfer coefficient. So you can increase the value of this H by providing some external cooling media. Like you can use the cooling fans. So if you use the cooling fans, the value of H will be increased. Or if you use some another cooling medium, then it is also increased. Also this delta T, where A is at atmospheric temperature, and if you decrease the value of this atmospheric temperature, automatically your delta T will be increased, and as the delta T increase, your HD will increase. So these are the some common precautions or the common ways that you have studied in heat transfer, how to control the heat generated. And whatsoever your heat is get generated, and the amount of that is get dissipated, and the remaining we call it as a heat carried away or taken away by the coolant. So what we can say, heat carried away or taken away by the coolant is Hg minus Hd, and which is given by mCp del T, where m is the mass of the lubricating oil passing through the bearing in kilograms per second. Cp is the specific heat of lubricating oil in kilojoules per kg degree Celsius, and delta T is the temperature rise in degree Celsius. So we will find out the value of this mass flow rate or mass of the lubricating oil in the equation, where m is equal to rho into q into 10 to the power minus 6 kilograms per seconds. Minus 6 is because the q is given in millimeter cube per seconds. That's why it has been taken it as a 10 to the power minus 6, because it should be meter. So it becomes kg per second. So this flow variable is given by, we know flow variable is q upon r c NaCl, and from here this equation will get the value of q. So q, value of q in terms of flow variable is this multiplied by RCNSL. So we'll substitute this value of q in the equation of mass. So m is equal to rho RCNSL into flow variable into 10 to the power minus 6 kilograms per second. And we'll substitute this value of m in this equation, mCp delta T. So m is substituted as rho RNSCL Ft into Cp del T. And what we can say that your heat generated should be equal to heat carried away. And equating these two equations, Hg is equal to Hc, will get delta T, that is the temperature rise, equal to 4 pi P upon rho Cp into Cft upon Cv. And generally this value of specific gravity is taken as 0.86, and that of Cp is taken as 1.76 kilojoule per kg. So here you can directly remember this equation. So temperature rise or the temperature difference of the lubricating oil is given by the equation 8.3 P, this is the bearing pressure, Cf3 upon Ft. So this is the way we can calculate the heat generated in the bearings, as well as heat dissipated and amount of heat carried away, or the mass flow rate of the lubricating oil. So as well as you can also calculate the temperature difference or the temperature rise in the bearing. So these are the way one can find out the heat generated in the bearings. Here the design procedure for the general bearing is I have listed. Just to quickly we'll see how the bearings are designed, and we'll go for one numerical so that you will get the idea how to design the general bearings. So this is the procedure where first the step is you should have to determine the bearing length by choosing the ratio L upon D from the table A. So here if you can see, this is the table A is given, and this table is giving you the design values for the general bearings. So here different machineries are given, type of bearings where they are used, and maximum bearing pressure also you can select from these values. You can select the value of absolute viscosity also in, from the table. Here that absolute viscosity is denoted by Z. We are using it as a mu. Zn upon P, that constant also you can select. C upon D ratio also you can select, and L upon D you can also select. So this table will give you the idea or the values of the difference. So L by D you can select diameter of this um, shaft where the bearing is you are going to fit is known to you, and from that you can choose the length of the bearing. So this is the one table which is helpful to you for selection of the different parameters. Second, you can check the bearing pressure. So P is equal to W upon L into D. So either you know what is the amount of radial load acting on the bearing, and L is you have selected, diameter is known, so bearing pressure you can calculate, and from the table you just take whether the value of that is suitable or within the limit for the given in the table or not. Then select the lubricant. So selection of the lubricant is from the table B, and here this is the another table which is given for the selection of the lubricating oils. So absolute viscosity of commonly used lubricating oils are given over here. So the type of oil, these are SAE 10, Society of Automotive Engineers, 20, 30, 40. These are the values 30, 35, 40, and different values of viscosities are given. So these are the temperature range. So suppose you are selecting particular oil, suppose SAE 50, and if it is going to operate at the temperature of 75 degree, what should be the value of your absolute viscosity that is given in the table. So this is the table which will give you the idea for the selection of the lubricant for your particular operating temperature, that is at what temperature you are going to operate your bearing. And this temperature should be between 26.5 degrees Celsius and 60 degrees Celsius, with 82 as a maximum for high temperature installation such as steam turbine. So here it is mentioned that the advisable temperature range is from 26.5 to 60 degrees Celsius, except in another cases it is 82. Then you should have to determine the operating value of mu n upon P, because P you know, n is know that what speed your bearing is going to rotate, mu that is the coefficient of friction, which is Z is shown in the table, you have selected, and check this operating value and for the assumed bearing temperature, and check this value with corresponding value given in the table to determine the possibility of maintaining the fluid film operation. So you know what is the importance of this mu n upon P. From the value of mu n upon P and from the graph coefficient of friction versus mu n upon P, which is given by Mackey's investigation, you should now decide in which region your bearing is operating, whether it is operating in film, boundary or thick film. So decide whether it is unstable region or in a stable region. Then next is assume the clearance ratio. Again the probable values of C by D are given to you. Then determine the coefficient of friction. We know the relation. This relation now is given by the Mackey's. So coefficient of friction is given by 2 pi square mu n upon P R upon P plus alpha. Determine the heat generated by the relation. You just now we have seen the heat generation is nothing but the power loss in friction, 2 pi ns FWR into 10 to the power minus 6 in kilowatts. Then determine the heat dissipated, that is by HA del T, and now you calculate the thermal equilibrium to see that the heat dissipated becomes at least equal to heat generated. So we have seen that your heat generated should be less than the heat dissipated. And if heat generated is more than the heat dissipated, then either your bearing is redesigned or it is artificially cooled. That now we already discussed. So these are the some references which I have referred for the preparation of this and quiz and answers.